Hello everyone. Today we're going to go through a few max and min problem examples. I've got 7 ready to go, but we'll probably split that up over a couple of videos so that it's a little bit more easy to digest. So anyway, I hope you have a spare sheet of paper or 2 on hand because you'll probably need it. So let's get started. So the first thing, general procedure with these questions. It is a good idea to first label variables for what is to be determined and a variable for what is to be maximized or minimized. Second, you should write an equation for what is to be maximized or minimized, and this may require some extra work to get it in terms of one variable. Third, you should take the derivative and determine the critical numbers. Fourth, you should determine whether the critical number represents a max or a min, and that generally involves taking the second derivative. And whether it's curve up or curve down will allow you to confirm if it is a max or a min. And fifth, you should write a concluding statement with units. So this first question, we need to determine 2 numbers whose product is 4 and whose sum of squares is a minimum. So we have 2 numbers, we'll maybe call them A and B. They have a product that is 4, so when they multiply, they give a product of 4, and their sum of the squares is a minimum. So we can call maybe the sum of squares, that's the thing we need to minimize. We can maybe call that S, and we require a squared plus b squared to be a minimum. Now this equation has 2 variables, so what we'll need to do before we go much further is write this in terms of a single variable, and that'll allow us to take the derivative a little bit more easily. So I thought we'd start this lesson with a bit of an exercise. I'm going to proceed through this example, and I don't want you to write this for now, and I want you to see if you can spot the error that I'm going to make. So first off, S is a squared plus b squared, and I'm going to rewrite one of those variables, either a or b, in terms of the other. So I'm going to go S equals a squared, and I'm going to get it all in terms of a. So it'll go like this. Next, I'm going to simplify that a little bit. A squared plus 4a to the minus 2. Third step, I'm going to take the derivative of this, derivative of s with respect to a. So ds dA is 2a dA, which is 1, minus 8a to the minus 3. Next, I'm going to set that expression equal to 0 and see if I can determine a max. So I'm going to go 0 equals 2a minus 8a to the minus 3. Next, I'm going to see if I can isolate for a. So I'm going to bring the 8a maybe to this side. So I'll write it like this, equals 2a. A little bit closer now, so now I'm going to multiply both sides by a cubed and divide both sides by 2. So I'm going to go 4 equals a to the 4th, and finally I get a is the 4th root of 4. And b, given that it's related by this equation, I will say that b is the 4th root of 4 cubed. So these 2 numbers should multiply to give 4. So if I write this in exponential notation, 4 to the 1/4, 4 to the 3/4 gives us 4. So what I would like for you to do now, especially if there's anyone within earshot that's unaware of what you're doing, is to call out your answer out loud. Either say, no mistakes, or number whatever. So maybe number 9. So I want you to just have a look through, maybe pause it if you need, to see what mistake, if any, were made. And I want you to call out your answer. Okay? Ready? Perfect. I can see that caught their attention if you did it. Now they know you mean business, especially if you said no mistakes. Now unfortunately there was a mistake, and it was right at the beginning. But whoever heard you say no mistakes doesn't know that. So the mistake was here, going from here to there. So let's see if we can fix it. So let's start by doing this properly. This squared needs to be applied to the 4 as well. Should look like this. A squared plus 16, a to the minus 2. Next we can take the derivative, this time of the proper expression. So by the way, you can start writing this now as well as this. That was fine. So ds dA will be 2a minus 32a to the minus 3. If we were to write this in a fraction form, it would look like 2a minus 32 over a cubed. So if I wanted to get rid of this term in the denominator, I could factor this out. So I probably should. So let's do that. So ds dA, I am going to factor out a 2a to the minus 3. So that will leave me with a to the 4th. So keep in mind, if I were to redistribute this back in, I should get that back. And then this would be subtract 16. Okay, and we can factor this. So ds dA is equal to 2a minus 3. And this is a difference of squares. So we could do a squared plus 4, a squared minus 4. And this is further a difference of squares. So that will now be 2a to the minus 3. A squared plus 4 doesn't split up any further. And then we'll have a plus 2, a minus 2. So my critical numbers as a result of this, same procedure, I'll let the derivative be 0. That will give me critical numbers. There's no real number for a that I could put in here that would give a 0. If I put a 0 in here, keeping in mind that that would be an a cubed in the denominator, so I could easily rewrite this as a cubed like that, right? If that was 0, that would be a problem. If I let either a be negative 2 or positive 2, that would give us 0 as well. So next thing we should do is take the second derivative. So do d squared s dA squared. So looking maybe above at perhaps this one, that's a little bit easier to work with. So it would be 2, and then negative 3 times negative 32, and then that would be a to the minus 4. So we would get then 2 plus 96a to the minus 4. So that would be 2 plus 96 over a to the 4th. There is no way that I can put a real number in here for a that would give me something other than a positive number. So this will always be positive. So because the second derivative is always positive, that means s is always going to be curve up. So what that means is these numbers will give me minima. Now, 0 times 0 does not equal 4, as was required at the beginning, right? We need ab equal to 4. So we'd get rid of that. Negative 2 times negative 2 is 4, so that should be fine. And 2 times 2 is also 4. So my answers here for this question that meet the requirements are either negative 2 and negative 2, or positive 2 and positive 2. Those are my options. In example number 2, we have 2,700 centimeters squared of material to make a box with a square base and an open top. We need to determine the largest volume of the box. So if we have a square base, that means these lengths are equal. We'll maybe call them x, and we need to figure out what the height is, so let's maybe call these y, and all of these should be equal length as well. The volume of a box is length by width by height. Now given that the base is x by x, we can say x squared, and then we need to multiply that by the height, which is y. So what we need to do is figure out what the maximum volume is. However, what we have currently is an equation in 2 variables. So we need to do our best to see if we can get these to be expressed in either all in terms of x or all in terms of y. So one other bit of information that we haven't used yet is this. So the area of the box is going to be x squared, that gives the base, and then we're going to have x by y, and we have 4 pieces that are x by y. So the surface area total expression will be x squared plus 4xy equals 2700. So what I might do now is, because I have an x here and an x there, that would be a little bit tricky to get it on its own. But I have only one y here, so I'm going to isolate this equation for y, and then I can sub it in for y up here. So isolating this equation for y looks like this. I would subtract x squared from both sides. That would get rid of that term, and then I would divide both sides by 4x, giving me this. So this is what I'm going to sub in for y here. And then I have an expression for volume entirely in terms of x. So volume now is x squared times 2700 minus x squared divided by 4x. So I'm going to get rid of the x in the denominator, leaving me with just 1/4 x. And then inside the brackets, what's left is 2700 minus x squared. And now I can take the derivative of this with respect to x. So I need to do product rule to this. So the derivative of the first is 1 times the second, which is 2700 minus x squared. And then I need to add the derivative of the second times the first. So times x, the derivative of the stuff inside the brackets is just going to be negative 2x. I can simplify the stuff in the brackets a little bit. So I would have 2700 minus x squared minus 2x squared. I can combine these x squared terms, giving me 1/4 negative 3x squared plus 2700. Both of these are divisible by 3, so I'm going to maybe divide out a negative 3, giving me negative 3/4 x squared minus 900. Now 900 is a perfect square. 30 times 30 is 900. So I'm going to factor this using difference of squares. So negative 3/4 x plus 30 and x minus 30. So my critical values are negative 30 and 30. If I set the derivative equal to 0, those are my two possibilities that will make the whole right side of the equation 0. Now, I don't know about you, but I've never seen a box with a negative dimension, so we can probably safely eliminate that option. And that means that y is going to be 2700 minus 30 squared divided by 4 times 30. So that would be 2700 minus 900 divided by 120, giving me 15 centimeters. And the length and the width should be 30 centimeters. Now it would be good practice to confirm whether or not this is actually a maximum point. So what I should do maybe is take the second derivative. So I'll start with this and take the second derivative and see what happens. So this would be negative 3/4, and the derivative of that stuff would be 2x. So negative 6x over 4, which would be negative 3x over 2. Now this is a linear function that passes through 0. So the second derivative is going to be negative for all positive values of x. And because the second derivative is negative for all positive values of x, that means it's curved down, which means this critical point is guaranteed to be a maximum. So on to the next question. Number 3, we need to determine the point or points on the curve y equals x squared that is closest to 18, 0. So I've already drawn a diagram here. We have the parabola y equals x squared. We need to find some point AB that lives on the parabola x squared that minimizes this straight line distance. So we can go ahead and maybe call this straight line distance S and see what we can do to express it in terms of A and B. So you may recognize this shape. It's a right angle triangle. We can express S in terms of A and B now. So the height of this triangle is going to be b. This length is a. This full length is 18. So the length of this other side of the triangle is going to be 18 minus a. Now I can write s in terms of a and b using Pythagoras Theorem. So I can write s squared equals 18 minus a squared plus b squared. Now unfortunately, we have two separate variables for this equation. So it would be a bit of a nightmare to take the derivative of this and have a's and b's floating around. So it would be helpful to get this all in terms of one variable. So we can use maybe the fact that this coordinate AB lives on this curve x squared. Because it lives on the curve x squared, for any a that I choose, this is going to be true. So I'm going to go ahead and sub a squared in wherever I see a b. So now the expression for s squared becomes this, 18 minus a squared plus a to the fourth. So the next thing we could do here, and maybe don't write this down, is take the square root of both sides of this equation and get an expression for s. So that would be fine, and then we could take the square root of this with respect to a, but unfortunately it's a little more complicated than it needs to be because there is a square root symbol. So a suggestion that I'm going to make here is rather than taking the square root of this s, I am going to rename the variable s squared, and I'm going to call it uppercase s. My expression for uppercase s will simply be 18 minus a squared plus a to the fourth. So if I find out there's a minimum at a particular location of a for capital S, it will also be a minimum for lowercase s. So next we're going to simplify this expression, and then we can take the derivative with respect to a. So if I expand this and gather like terms if I can, I end up with this, a to the fourth plus a squared minus 36a plus 324. And now I can take the derivative with respect to a. So that'll be 4a cubed plus 2a minus 36. I can simplify this a little bit by removing a 2 from everything, leaving me with 2a cubed plus a minus 18. So it would be helpful at this point to know that a 0 for this is 2. So a equals 2 is a 0 for the thing in brackets here. So now I'm going to use synthetic division to help me factor this expression. So remember, I do not have an a squared term in here, so I need to have a placeholder of 0, 1a, and negative 18. So proceed with synthetic division, drop the 2. Negative 2 times 2 is negative 4. 0 subtract negative 4 is 4. Negative 2 times 4 is negative 8. 1 subtract negative 8 is 9. And negative 2 times 9 is negative 18. And then 18 subtract negative 18 is 0. So now I'm going to simplify this a little bit. So my expression for the first derivative of s with respect to a becomes this, 2a squared plus 4a plus 9. I'm going to tell you that there are no real roots for this expression, which you can confirm. So the only critical number here is a equals 2. So a equals 2 looks like a safe bet, and given that we're on the curve x squared, a, remember, was my value for x. So that means the y coordinate should be 4, right? 2 squared is 4. So I suspect that 2, 4 is as close as we can get on the parabola to the point 18, 0. Now, I probably shouldn't quite jump the gun just yet. I should check that we have a second derivative that gives us a minimum. So the second derivative of this would be 12a squared plus 2a. And there is no value of a that I can pick that is a real number that will make this a negative number. This is always going to be positive, which is good because that means that this function s is curve up for all values of a, which means that this critical value I found earlier is indeed the coordinate that minimizes the distance to 18, 0. So that's our final answer. And last question number 4. We're looking to determine the radius and height of a right circular cylinder of largest volume that can be inscribed in a right circular cone of a radius of 6 and a height of 10. So we're looking to fit the largest possible cylinder underneath this cone. So I guess ultimately what we need to do is minimize this quantity, V cone minus V cylinder. This quantity needs to be the smallest possible. The height and the width of this cylinder is constrained though, so I can't just pick any value for R and H that I want. So we can start maybe by writing the formula for the volume of a cone, which is 1/3 pi r squared H. And these are both fixed. The radius is 6 and the height is 10. So we can sub in for the radius and the height, giving us a volume of 120 pi centimeters cubed. So next I can write the volume of a cylinder. This is on your formula sheet, given by pi r squared H. We do not yet know R or H. These are variable, but they are constrained. So the constraint is I need to select a cylinder that will fit comfortably underneath this cone. So let's maybe have a look at this from a different perspective. I've indicated the cylinder with yellow here. So this is half of the cylinder. There would be another half over here. Peak of the cone is at 0, 10. The foot of the cone is at 6, 0. This upper edge of the cylinder has to live on this inside surface of the cone. So what I need to do is come up with an expression for the volume of the cylinder in terms of one variable. So currently it's R and H. It would be nice to express one in terms of the other. So what I'm going to do then, come up with an expression for R and H. So this is a straight line. The slope of it can be determined. So the rise is, it goes from 10 to 0. So the rise is -10 and the run is 6. Which can be simplified to -5/3. That's the slope. Now I can come up with an expression that relates R and H using slope-intercept form. So H is going to be given by the slope, -5/3 R, plus the intercept, which is 10. So this line is given by this equation, and that relates R and H. So now I can take this and use it to simplify this in terms of one variable. So I'm now going to express the volume of the cylinder using only one variable. So I'm going to keep R squared, and I'm going to sub now H is -5/3 R plus 10. And now I can take the derivative of this with respect to R and see if I can come up with some maximum volume. The first derivative with respect to R will be pi times 2r times -5/3 R plus 10. And then I need to add R squared times -5/3. So I've just used product rule there. And I can simplify this a little bit. So I would eventually get -10/3 R squared plus 20R minus 5/3 R squared. And I can group like terms, giving me pi times -5R squared plus 20R. I can factor out a -5R from this. And then I'm left with R minus 4. So if I set this equal to 0, that will allow me to give a critical value. So one critical value will be R equals 0, and the other critical value will be R equals 4. Now, if we have a cylinder with 0 radius, we basically have nothing. So that we can basically eliminate is nonsense. And our radius of the cylinder should be 4 centimeters. So it would be prudent for us to check that this is indeed a maximum. So we should do the second derivative. We can maybe use this one. It's a little bit simpler. So it would be pi, and that would be -10R plus 20. So as long as we have positive values for R, it is concave up between 0 and 2, I believe, and it is concave down on the interval from 2 to infinity. And given that radius that we found is on this interval, it's concave down there, so this should be a maximum. So it's always a good idea to confirm whether or not this gives you a maximum using the second derivative. So my relation for h and r, I can sub in 4 for r, giving me an h of 10/3 centimeters, or approximately 3.3 centimeters. So the dimensions of the cylinder, the radius should be 4, the height should be about 3.3 centimeters. So that's it for today. At this point, I would encourage you to look at the textbook questions on page 188 and have a look at numbers 1 to 11. See you next time.